Welcome to Lesson 17, Current, Charge and Resistance. Today we start electricity, and we start from absolute first principles. Here's the plan for today. What does a circuit actually need in order to work? It needs two things. First, a closed loop, an unbroken path so the charge has somewhere to go. Break the loop and everything stops. Second, a potential difference, something to push the charge around, driving it from a high potential to a low potential. A loop with no potential difference is a road with no traffic. A potential difference with no loop is a push with nowhere to go. You need both. Current is the flow of charge carriers. I find the river metaphor helps. What matters isn't the individual water molecules, but the total amount of water flowing past a point each second. Same with current. We don't care about counting individual electrons, we care about the total charge per second. That's why current, I, equals Q over T. There are two facts to bank. The charge on a single electron is 1.6 times 10 to the minus 19 coulombs, a tiny number, which is why you need so many of them. Secondly, conventional current is defined as flowing from positive to negative, which is, awkwardly, the opposite direction to the actual electron flow. But that's a historical accident, but it's the convention, so we use it. Whether a material conducts comes down to whether its electrons can move. In a conductor, a metal, you've got that sea of delocalized electrons we met back in the photoelectric lesson, which are free to drift so charge flows easily. In an insulator, however, the electrons are locked to their atoms. You can apply a potential difference and nothing happens because there's nothing free to flow. And then a semiconductor sits in between with an interesting twist. It conducts better as it gets hotter. This is because the heat releases more charge carriers, unfreezing them, so more current can flow. That's the exact opposite of a metal, and we'll see why that matters next lesson with thermistors. Now, potential difference. Let's define it properly, because voltage gets used very loosely. Potential difference is the energy transferred per unit charge. V equals W over Q. Rearranged, W equals QV. The metaphor I like is a waterfall. The potential difference is the height of the drop. Every coulomb of charge that falls through it gives up an amount of energy set by that height. Bigger potential difference, bigger drop, more energy delivered per coulomb. So what actually is resistance? It's a measure of how hard it is to push a current through something. R equals V over I, measured in ohms, given the symbol omega. Read that equation as a story. It tells you how much push, how many volts, you need in order to drive 1 amp of current. If a component has low resistance, a small push gives you a decent current. If it has a high resistance, you need far more push for the same current, because more energy is being lost getting the charge carriers across. That's resistance, the energy cost of getting charge through. Finally, power. Power is energy per second, so it's W over T, but W is QV, and Q over T is just the current, so power equals IV, current times voltage. Quick question. A lamp running at 4 volts, carrying 1 amp. What's its power? 4 watts, I times V. And by substituting V equals IR, you can also write power as I squared R, or as V squared over R. 3 forms of the same equation, use whichever matches the quantities you've been given. That's the end of the video. Thanks for watching, and check out my tutoring page below.